This is my physics lab 4 on oscillations. So the goal of this experiment is to compare predicted motion using a glow script code with the observed motion of an oscillating mass attached to a spring. The results of this experiment is that the total change in energy is 0, demonstrating the energy principle, and the predicted model and observed model also offer very similar data, meaning there is not too much error in the data. So the fundamental principles I used was Newton's second law, the idea that net force is equal to change in momentum over change in time, or mass times acceleration, from which you can derive the velocity update formula and the position update formula. I also used the energy principle, the idea that the energy of the system is equal to the work of the surroundings plus the change in energy or the change in temperature. And then the change in energy of the system in this particular example is equal to the change in kinetic energy plus formulas over here, plus the change in gravitational potential energy, formulas right here, and then plus the change in potential energy of the spring, which the formula is right here. So here are my observed results. For the video tracker, my system is the weight, the earth, and the spring. My surroundings we assume to be nothing. The calibration is stick is set to 0.7 meters, which here acts as the length of L. The origin of my axes is set at the base of the spring. My initial position is negative 0.106 in the x direction and negative 0.649 in the y direction. And then my initial velocity is 0 meters per second square, or 0 meters per second. Here's how I found the initial conditions of the period, the spring stiffness, and the relaxed length. So for the period, I found 3 periods are outlined right here, and I divided it by 3 to find an average of 1.54 seconds, or 1.524 seconds. And then I used this formula that the period is equal to 2 pi times the square root of mass over the spring stiffness to find the spring stiffness of 6.83 Newton meters. And then I used this in the assumption that the net force is 0 because the mass should be having a constant velocity and thus not accelerating. So the force of gravity is equal to the force of the spring. So the relaxed length is equal to 0.123 meters. And then for my glow script code, here are the initial conditions of the mass of the ball, the position, initial velocity. And then my constants are right here. Here, the spring constant and the relaxed length of the spring I found in my tracker video. And then these 4 lines for energy, kinetic energy, potential energy are from the fundamental principle formulas. And then here is my computational loop to find the change in the energies. You can see all over here. And then here are the calculations of the energy changes, which again are just formulas from my fundamental principles. And then here are my graphs that I got. You can see the change in potential energy of the spring in green, of potential energy gravitational in red, the change of kinetic energy is blue, and then the total energy is in orange here. Then you can see the difference in the X and Y positions versus time of the model in blue and the experiment in red. There's some slight differences that I will go into later. So what does it mean? For my model system, is the energy principle satisfied? Yes, the energy principle is satisfied within the computational model. Since there are no external forces acting on this isolated system, the change in energy will always be 0. See, all of these changes in energy are going to cancel each other out to equal a total change in energy of 0. And what does it mean? So here are my 2 separate estimates of oscillation periods. So my estimation in X is taken from 3 oscillation periods, dividing it by 3 to get about 1.519 seconds. And then the same in Y to get about 1.330 seconds. And the difference here could be attributed to slightly incorrect tracking or the effective drag force that I don't account for in my experiment or in my model. Additionally, these 2 differences could contribute to slightly different spring constants and thus relaxed lengths, which again contributes to this difference that you see here. And then my possible sources of error. The initial velocity could have been slightly greater than 0 due to the mass being moved into its initial position by a person, and there's not much time to guarantee the mass is not moving. Other forces, such as drag force, were not accounted for, and thus the assumed work of the surroundings and change in temperature were most likely not 0 in both my model and my experiment, showing differences in actual change in energies. There are also errors that will occur from marking the center of mass of tracker, since it will never be completely accurate and is merely an estimation. So these all show the differences between the computational model and my experimental model.